Hello, everyone. We're getting to a close of this chapter on public key encryption. After that, the only regular topic will be on digital signatures, which we will cover next week. And after that, you're going to learn how to really do stuff by my colleague, Kas Kremas. Right. Right. Good. So now we're following the same conceptual steps as we did in the world of private key crypto, right? The last thing we looked into there in for encryption, at least, was chosen ciphertext secure encryption. As a matter of fact, we only looked into this after we had already covered authentication, because in the world of private key crypto, we needed authentication primitives, message authentication codes to build chosen ciphertext secure encryption. Here, it turns out we can using a little magic, we'll see we can get around using additional authentication, but let me not get ahead of myself. But discuss with you why chosen ciphertext security matters, maybe even more in the public key setting. So again, what's the point of chosen ciphertext security? Well, we want to protect against active adversaries, right? So active adversaries are adversaries who don't just eavesdrop on us, but who actually manipulate the messages that we send and try to gain an advantage by doing some clever modifications of the ciphertext that we've sent, observing behaviors of honest parties who try to decrypt this and get some information from this. And here's the thing: so in the public key setting, chosen ciphertext attacks are really a way bigger concern as in the private key world, as receivers expect messages from unknown senders, right? So in the private key setting, we had at least the option to authenticate things, but here, when you're a web server and you're being sent queries by internet users all over the world, you haven't met these people before, you don't have a shared secret with them, they're unknowns to you, but still we would like to protect the privacy or the secrecy of their queries to such a web server. Good. And let's consider a very simple scenario, right, where a web server just signals to the user if a ciphertext is valid or invalid, right? We need some mechanism like this because the network connections that we use, they are sometimes faulty. Think of a Wi-Fi network, you have packet loss. This is stuff you can't avoid. So sometimes a message that you send to a server just doesn't arrive there in its entirety, right? So you need to have some kind of fault tolerance or error tolerance against packet losses and similar things. That means typically these protocols, these web protocols by which servers communicate with clients have a built-in mode that says, okay, I didn't get the entire last message, please resend. So the server has a way to signal to clients that he couldn't decrypt something, right? That maybe the packet got distorted or something happened and please resend. So we just model this as follows. Let's think we're sending we're sending ciphertext to servers, And these ciphertexts can either be valid or invalid. We don't care about how they in any special case can become valid or invalid. We just care about that there's a server who in some way signals that he couldn't decrypt, that the ciphertext that you sent was invalid. Maybe this valid/invalid message can come in the form of a resend message, right? That the server tells the client, please resend. And I mean, I said it before, servers are essentially idiots, right? It's quite hard to teach servers to detect suspicious behavior, that if somewhat similar ciphertexts come and they are all apparently invalid, why should that be suspicious? That's really hard. Don't think that this server has sort of the capacity of a human to abstract that he's being tricked into something, into doing something which he actually shouldn't do or wouldn't like to do. So now that we've set up the scenario, let's look into a very concrete example. The so-called RSA public or RSA PKCS standard 1, or the S. The S stands for standard, so this is the RSA public key crypto standard number 1, which look as follows. So we've already looked at the textbook RSA scheme, right? And we know a textbook RSA is insecure or shouldn't be used or isn't even an encryption scheme, because encryption is deterministic, right? We know encrypting deterministically is bad. That doesn't give us any good security guarantee. So people knew this. People knew this in the 1980s and thought, okay, what we have to do when someone gives us a message, we have to randomize it, right? So the simple idea was, when you get a message M, don't just encrypt M itself, but encode M together with some randomness, and then encrypt this using textbook RSA. So the way this encoding function works is as follows. So let's say our RSA modulus n has or size of n is roughly k bytes, right? Or 8k bits. So k doesn't stand for kilo here. It's just this this integer here. So we're having an 8k bit integer. Maybe I'm taking a different color, and we're doing the following. In the lowest order bits, which I'm going to write to the right, we're going to put the message M. Okay, so separated by a 0 byte. So and this is followed by some R where we use 48 bits as a matter of fact. So here we have this randomness, but the point of all this together will be that this encoding randomness in the somewhat high order bits and the message followed in the somewhat low order bits, this will be a bit string of length here, this 8k minus 2 bits. And that sort of, when you think of it as a number, is a number this is smaller equal to, or in fact, truly smaller than 2 to the 8 times k minus 2. All right. And here's now this peculiarity about PKCS1, which we'll see in a moment ruins everything, right? So some engineers thought it was for whatever reason, right, to give maybe some well-formedness guarantee of the encrypted message, that the highest bits of this encoding should first be a byte of zeros, right, to 8 0 bits, followed by a binary encoding of 2. So now it's not 8 0 bits, but the 0x2 is just 0, 1, 1, 2, 3, 4, 5, 6, right? This is a byte encoding the number 2. Someone thought this was a good idea for whatever reason, and maybe on a meta level, because that person thought, for whatever reason, thought it was a good idea, is one of the reasons you're actually having to take this lecture here, right? So someone made a seemingly innocuous design choice in this standard, which had, as we will see in a moment, pretty drastic consequences. And such that if you ever happen to be in the situation of this person, then you should know that even such seemingly innocuous decisions can have drastic consequences, and you will maybe think twice about it, or then even better, talk to someone else, discuss this with an expert, and see if your design idea actually is good. Right, that's the right thing to do. Don't make the decision all by yourself. Talk to someone else. Sort of bounce your idea around. This is maybe something that didn't happen sufficiently here. Okay, so that's just the message encoding function. Everything else essentially works like in textbook RSA. So the keygen is in as in textbook RSA, and the encryption now also as in textbook RSA. The only difference, of course, being that we don't compute m to the e, but pkcs of m to the e, right? Where pkcs is a randomized function which chooses this every time we call it this string r here at random, right? And the output, since our integer n is of 8k bits, this pkcs of m, we can interpret this here as a number in Zn, right? So pkcs, think of pkcs as a function which maps bit strings of length. What did we say? Something, right? Whatever the here the correct message length is, doesn't really matter to let's say to the n to Zn. All right, good. And now decryption. Whoops. Decryption. Okay, let's. That doesn't look good. Let's read. This is in Zn. Decryption just does the following. Given a ciphertext C, it computes C to the D. Sorry, there's a typo. And now it just has to check if this M prime that we computed as C to the D is actually a correct PKCS encoding. Meaning that it starts with starts with some zeros. Then comes this 2 byte, then comes randomness, whatever, and then comes this 0 block. And if so, if this is a correct encoding, output M. I see there's a question in the chat. It seems like PKCS removes the advantage of having a smaller ciphertext that RSA has over El-Gamal. This is not necessarily an advantage, right? I mean, RSA isn't really okay. I hope I'm not wildly wrong here, but RSA is, in terms of key sizes, anyway much worse than El-Gamal type schemes when they use these special elliptic curves. So really, the advantage of El-Gamal here is to just have RSA is essentially to have another assumption. And quite frankly, when you use hybrid encryption, as we saw last lecture, then really the public key ciphertext size is not the biggest issue, right? I mean, right now we're discussing history. RSA PKCS1 has long been deprecated, right? Since more than 20 years. Okay, so our can you still hear me? Can someone say something if you can hear me? Yeah, because something said that my my connection was severed, but apparently it's not, which is good. So decryption first decrypts the ciphertext C, gets an M prime, and checks if M prime is a valid PKCS encoding. If so, it just outputs M. Otherwise, it outputs invalid. Okay, yeah, it seems my when I go on with my slides, this okay, I was disconnected from Zoom, which is bad. Sorry for the quick break. Let's see if this works. All right. Whoops. Sorry for the quick interruption. Zip. Okay. Good. Now let's share my screen again. That seems to work again. Okay, good. We're back here. Let's go forth. So we have the following observation, which will now be absolutely crucial. So such an M prime is a correct PKCS encoding, right? If and only if 2b is smaller than M prime is smaller than 3b minus 1, where b is just this 2 to the k minus 2 times 8, right? Why is that so? So if you look at any PKCS encoding, it starts, it's an 8K bit string, and your M prime starts with a leading 0, then a 2, and then essentially something, right, in base 8. Let's say 0 to something in base 8, right? In base 8, and this something is of a fixed length. So 0, well, that's just 0, but this 2 is essentially what when we're doing this in base 8, this is just multiplied with this is 2 times 2 to the k minus 2 times 8, which is just our b, right? So this is just 2 times b plus something, right? The lower order bits. And now, of course, we know that the lower order bits are smaller than whatever is there as a number is smaller than B. Plus, let's call it Z, where Z is smaller, where 0, of course, is smaller equals Z, is smaller than B minus 1. So on the lower end, Z is 0. On the higher end, B is Z minus 1. So you have that 2B is smaller equal M prime is smaller equal 3B minus 1. So we have that M prime, a correct PKCS encoding has to be in this interval 2B, 3B minus 1. Good. Right, so you have here M prime element 2B, 3B minus 1. And this was exploited by someone called Bleichenbacher, some 20 odd years ago. And let's see how this attack against PKCS works. And remind you, we're talking about chosen ciphertext attacks right now. So, of course, this will be a chosen ciphertext attack. So it turns out RSA PKCS, or in RSA PKCS1, a server which signals if a ciphertext is valid or not can be abused to implement a full-blown decryption oracle, right? So a server which tells you, this was a valid ciphertext or this was an invalid ciphertext, this tiny little bit of information essentially can be used using several queries to reveal the entire message encrypted in some ciphertext. So let's quickly see how does this work. Let's see, we have our friend Alice here, who just wants to talk to a web server, encrypting a message M and sending this ciphertext to the server. However, her as this is in the case in these man-in-the-middle attacks, her ciphertext is intercepted by the adversary, right? Who wants to learn what is M? Okay, what can he do? Well, of course, he can't just open the ciphertext, right? Let's assume RSA in itself is secure. So now he has to somehow use the server. And the way this is done in Bleichenbacher's attack is he will choose a small integer s. And this s has to come from a certain specific range. And now he computes another ciphertext C prime, which is C times s to the e modulo n. And now he sends this ciphertext C prime to the server and monitors if the ciphertext is valid or not. Maybe the server will tell him that the ciphertext is valid. If the server tells him that the ciphertext is valid, then he remembers this S. Then he's going to do something with this S. If this ciphertext is invalid, he just throws S away, or S and C prime away, and tries a different S. Right? He does this so long until he gets a valid. He gets the response from the server that C prime is valid. And all of a sudden, once he got valid or the information that C prime is valid, he learned something. What is E? Someone asks in the chat. The public key of RSA is N, E, right? And the secret key typically N, D, right? So you encrypt. I mean, let's go back, right? In PKCS1, you encrypt by computing PKCS of M to the E. Okay, so E, N is the public key. Good. So all of a sudden, if my adversary got the information that C prime is valid, he learned something. So the first, what he gets from that is that whatever C prime encrypts is a valid PKCS encoding. And now I'm claiming that the message or the message that's encrypted here is actually M times S. I mean, M here also contains all the randomness part of the PKCS encoding. So I'm not, so I should actually call this M prime here, right? This is not M, but M prime. And why is this the case? How do you learn that all of a sudden M prime times S is valid or is in this interval? Well, let's see. Our ciphertext C, I'm leaving the modulo n away for the moment, is just M prime to the E modulo n, right? Because what we do when we encrypt M, we first encode M into M prime, and then we raise it to the power E. But now C prime is just S to the E times M times C, and C is M prime to the E, which is just S times M to the E. And now the server told us that this is a valid ciphertext. And for valid ciphertexts, it means that whatever is here, sorry, this is of course M prime, this S times M prime, we've seen on the last slide that your ciphertext is valid if and only if this thing that's under the E here is in the interval 2b 3b minus 1. Good. So that's the additional information that you've learned. But of course, we can also assume that the original ciphertext that Alice sent is also valid, right? That means not M, but again, M prime, the PKCS encoding is also in this interval 2b 3b minus 1. Okay, so what does this information help us? How can we, if someone was to tell us, well, M is in this interval 2b, 3b minus 1, and M times S, for an S that I know, is also in this interval 2b, 3b minus 1. How can I recover M prime from that? Well, I cannot directly recover M prime, but let's look what's happening here. Let's draw our integers between, let's say, 0 and n on a line, right? And the first thing is, let's say we have this interval 2b, and let's say here somewhere 3b 3b minus 1, right? So I'm writing this as an open interval. So we know valid ciphertexts are basically RSA function applied to some message which is in this interval. Okay, so for starters, we know that our friend M prime is in this interval. Okay, good. But we also know, since the ciphertext told us that C prime is valid, we also know that S times M prime modulo n is in this interval. Okay, here I'm writing now mod n because multiplying with S could and should cause a modular reduction. But what does it mean that S times M lies in this interval? What does that mean? What does that say about S times M? So if I have S times M prime mod n element to be, let's write it 3b, right? That means, of course, there exists, we can say, without loss of generality, positive integer r, such that s times n prime minus r times n is in this interval here, 2b comma 3b. And now we can rewrite this. This is actually an equivalence. This just means that s times m prime is in one of these intervals, right? 2b plus r times n, comma 3b plus r times n. Right, I've just rewritten things. And what does that mean for the picture? Well, for r equals 0, this is just this red interval that I've drawn. But for instance, if r equals 1, let's just extend our number line. Let's make it roughly proportional. We're here in 2b plus n, going further 3b plus n, right? And we can go do that even further. So here we have 2n, here we have 3n. Here we have 2b plus 2n and 3b plus 2n, right? So we kind of know that this s times m prime is either, by the way, let me do the other one here, green. So we know that m prime is in the green one, and s times m prime is in one of those guys, either here or there, and so forth. Okay. S times m prime is in one of these intervals. So there's a question in the chat, but how can we get a correct S in non-negligible time? Is it so easy? In fact, yeah, the thing is, B is this interval b comma 3b is actually quite big. If you choose sort of a random number, then in fact with constant probability you land in this interval. So if you choose S somewhat random, or if you try a few, then with very high probability very soon you will get such an S. So the point why this works is because this interval 2b, 3b is really big, right? I mean, here, this is of course not drawn to scale, but it looks like it covers almost half of what you have of the numbers between 0 and n. It's not half, but it's a large fraction. It's in fact a constant fraction. Good question. So now we know that S times M is in one of these guys here, right? One of these orange intervals. What does that tell us about M prime? If we know that S times M prime is in one of these intervals, well, now we're computing over the integers, right? So what? Oh, sorry, no, that's too much. Let's just go until n. If we know that S times M prime is in one of these guys, we can just scale them down, right? Then M must be in one of the scaled down versions of these intervals. So if we take this interval and essentially, let's use a different color for this, maybe black. Now my writing interferes a little, but we scale this down by a factor of S and get an interval here. We do the same with this guy, right? Scaling it down with a factor of s gives us 1 here. And also this guy here, right? And for my example, let's just stop here. We get that our m, and now I'm using maybe black. If s times m is sorry, s times m prime is in one of the orange ones, then m prime must be in one of the black ones. Okay, so basically, I could now just scale these intervals or this union of intervals down to a smaller union of intervals until I'm somewhere between 0 and n, right? And here's the point: because the original intervals couldn't be so big, right? We know that this interval here had a size of b, but we're scaling it down with a factor s. So here the size of this one here is b divided by s. Okay, so each of these guys has size b divided by s, but they're all disjoint. And s is rather small, which means if s is not too big, you will only get a small number of intervals here. In my case, it's 3, right? But essentially, what that means is you're getting s intervals here. Intervals each of size each of size b divided by s. Okay, so, and we know that m prime is in one of these intervals. But we knew from before, let's go back to that green interval, that m prime, because C is also a valid ciphertext, that m is also in this interval, right? So we get that m prime is in the green thing, but m prime is also in one of the black things, right? So what we can do is we can intersect the two. So we know that if m prime is in both, then what happens? Sorry. Okay, my bad. That means m prime is also has to be in this red interval. So the consequence of this is now we could now we've increased our knowledge about m prime by confining it into an even smaller interval. Now just repeat this a few times for different s, and these intervals become smaller, rapidly smaller and smaller. Might be that you have to make a heuristic assumption, but sort of just do this a few times and you will find m prime precisely, right? You will confine m prime to a single point, right? So it's in these smaller and smaller intervals. Doing the math here is a bit, it's not really hard, but a bit annoying, right? But what you will get is, in the end, an interval which just consists of a single point and contains your point m prime. And like this, just by okay, good. So someone's asking the question: could you explain how it is possible to create those little black intervals. Good. So thanks for asking a question. If you had a problem there, maybe someone else had the same question. So we know that S times M is in this interval, or S times M prime as an integer, is in this interval 2b plus Rn, 3b plus Rn, right? And these are the orange intervals that I was drawing there. So from this is equivalent just by dividing both sides by S, that M prime is in the interval 2b plus Rn divided by S, comma, 3b plus Rn divided by S. This is not including this, not including the right side, right? So if S times M is in this large interval, then, or in this somewhat shifted interval, then M prime is in the scaled down interval. This is what I was drawing with these scaling down operations. Good. So M prime must be in one of these scaled down intervals. But I think the picture where we really scale down these intervals kind of captures what's happening there. But good. So this is Bleichenbacher's technique, coming up with these sets of intervals, scaling them down, concluding that in one of these scaled down intervals, our M prime must be, and just intersecting it with what we already know about M prime, namely that it's in this other interval here. Okay, so this is really just a high level idea, which should tell you why this PKCS encoding was such a bad idea, right? So from an engineer's perspective, it looked like innocuous, letting it start with a 0 and a 2, this encoding. But what this meant if you translate this into the underlying algebra is that correct encodings are confined to this interval 2b, 3b. Okay, which was really cleverly exploited by Bleichenbacher. All right, so now you should see why, let's say, CCA security really matters. And since we have that out of the way, let's define chosen ciphertext security for public key encryption. And of course, it again works analogously to the private key setting. We have an adversary and a challenger. The adversary, someone is asking me privately on the chat, does this have anything to do with the 0x02 earlier mentioned? And the answer is, of course, yes. The 0x02, as I've discussed earlier, makes sure that, let's go back, we have a bit of time. This let's use a different color, that your encoding M prime is of the form 2b plus z, where z is between 0 and b minus 1. So this 2x part of the encoding here sort of makes sure that correct PKCS encodings are in this interval 2b to 3b minus 1. Someone is asking, the blue interval below is not scaled down, only the black. Am I right? We have 0 to 3n. Good. Why did we scale down? Why did we only scale down these orange intervals into the black ones? So the reason is we have S times M. Right? Just look at, again, these intervals here. So the information we get is that M prime is in one of these scaled down intervals, because we have S times M prime, we don't have S times N, right? S times N doesn't occur anywhere, it's just this S times M prime. So that's the reason only these orange intervals are scaled down. Okay, but we're halfway through the lecture. I should get or a little bit more than halfway. I should I should continue with this stuff. So good. What am I doing? Okay, how does the IND-CCA experiment work? We generate a pair of public and secret keys, give the adversary the public key, as in the public key in CPA experiment, and now we give him access to a decryption oracle, right? Where he can send ciphertext CI, decryption oracle decrypts them, and answers with messages MI. At some point, he just announces two messages, M0 and M1. The challenger does the usual, flip a random bit B, encrypt MB, and give him C star. Then in the second phase, we give the adversary again access to a decryption oracle, which decrypts every ciphertext except the challenge ciphertext, right? C star is not decrypted. Everything else is being properly answered by the decryption oracle. And in the end, the adversary has to provide a guess B prime for B, and he wins if he guesses B correctly. And as usual, we say an encryption scheme, keygen EncDEC is IND-CCA secure now, CCA for chosen ciphertext attacks secure if it holds for every PPT adversary A that there's a negligible function nu, such that for all security parameters lambda, the winning probability of the adversary is at most 1/2 plus nu. Okay, that's chosen ciphertext security for public key encryption. But last lecture, when we talked about hybrid encryption, we've also seen this notion of key encapsulation mechanisms, right? So it's, since we've learned that key encapsulation mechanisms are, in some sense, the right way to use public key encryption or to use public key primitives, let's also define IND-CCA security for key encapsulation mechanisms, all right? So idea is the following. Again, we generate our public and secret keys, and now we directly encapsulate a key because for chems there's no messages. Choose a random bit B. If B equals 0, set K star to be just the key we just generated. Otherwise, choose a fresh key, and now we just give the adversary PK, C star, and K star. And now the only difference to the IND-CPA experiment for chems is that we give the adversary a decryption oracle, right? If CI, which decrypts, of course, or decapsulates the caps, this should actually be, decapsulates every ciphertext except C star, right? And here, let's call these guys not MI, but KI. In the end, he has to guess the bit B, whether the which signals whether the key K star that he got actually is the key that's encapsulated in C star, or if it's just a fresh uniformly random key. And again, the same thing. If he guesses B correctly, he wins. And we say that a chem is IND-CCA secure if, again, for every PPT adversary A, there exists a negligible function nu such that for all lambda, his winning probability is bounded by 1/2 plus nu of lambda. as before. We've seen by now really many of these definitions. We're still kind of seeing 2 more next weeks, but we're almost done. Okay, good. So last lecture, in the lecture on hybrid encryption, we have seen how an IND-CCA secure KEM combined with an IND-CCA secure private key encryption scheme gives us an IND-CCA secure or an IND-CCA secure public key encryption scheme. So now the natural question is, what about CCA security? Does this work in the very same way? And the answer will be yes, given that the primitives that we use have the proper security. So let's say a keygen encaps decaps is a key encapsulation mechanism. EncDec is a private key encryption scheme. Then just recall from last time, we have constructed a public key encryption scheme, keygen prime, enc prime, dec prime as follows. Keygen prime just does the same as keygen. It creates a pair of public and secret keys for the key encapsulation mechanism. Enc first runs the encaps algorithm to get a ciphertext header C1 and a symmetric key K, and then it uses the symmetric key K to encrypt the message M with the symmetric key encryption scheme. And dec prime really does the same thing as before. Given a ciphertext consisting of header and payload, it first decapsulates the symmetric key K from the ciphertext header, and then uses this symmetric key to decrypt the payload part C2. And just very quickly, let's assume our key encapsulation mechanism is IND-CCA secure. And furthermore, that now the private key encryption scheme is also IND-CCA secure. So now we need IND-CCA security from both components, from the key encapsulation mechanism and the private key encryption scheme. Then this gives us a IND-CCA secure public key encryption scheme. So the thing is, the proof for this theorem is somewhat tedious and time consuming, right? Proof is tedious and time consuming. The issue is it needs to go through quite a few cases, right? You need to distinguish quite a few cases, and I think the learning effect for this proof is not as big, but it essentially mimics the proof that we've sketched last time for CPA security with just the additional challenge of having to simulate the decryption oracle, right? Both the when we use the security of the KEM, we get a decryption oracle, and of the private key, the IND-CCA secure private key encryption, there we also get a decryption oracle. So that's the, I mean, believe me, things come together. If you really want to know it, you can just look this up in the book, and let me just write that down for you. This is on page 398. 398. Good. Oh, actually, no. So even Katzlinde doesn't provide a proof. I mean, they say a proof is obtained by a suitable modification of the proof of theorem CPA part. So yeah, maybe try to do it as an exercise, but it's really not that hard. It's a bit tedious, but it's not really insightful. All right. Good. Okay, so now we know that all we have to get are IND-CCA secure key encapsulation mechanisms. So let's build ourselves an IND-CCA secure key encapsulation mechanism. Then with this hybrid encryption construction that we've just seen, we get IND-CCA secure public key encryption. Okay, and now we're gonna build that from the RSA assumption, right? And I have talked about textbook RSA, but not really about the assumption, what it means for RSA to be secure. So I have talked about the factoring assumption, which, given two random large primes P and Q, try to factor your N. It turns out we don't know whether hardness of factoring implies hardness of of the RSA problem, which I'm going to define now. So that's the reason why we need to make this explicit RSA assumption that you will see here. Good. Consider the following experiment. First, we generate an RSA modulus n together with this E and D, right? E times D is congruent 1 modulo phi of n. This is just the textbook RSA keygen. So what I write as RSA gen here is just textbook RSA keygen. I mean, I wrote it down here. Next, we do the following. We choose ourselves a random R in Zn and set C to R to the E mod n. Basically, what we're doing is we're choosing a random message R and encrypt it with textbook RSA, right? Choose random message R and encrypt with textbook RSA. Now, I am giving the resulting ciphertext to the adversary, who computes an R prime and wins if R prime to the E is the same as C. There should be a white space here. If so, we output 1, otherwise 0. Essentially, since we know that for correctly formed RSA moduli, R to the E is a permutation, we could equivalently check if R prime equals R, right? But I mean, for reasons that sort of become obvious in the reduction, it makes more sense to check whether R prime to the E is C, right? Because our reduction will not know what R is, but it does know what C is. So that's the RSA experiment, and the RSA assumption or RSA conjecture states that it holds for every PPT adversary A that the winning probability of such an adversary in the RSA experiment is negligible. So RSA assumption really just states that take textbook RSA and don't encrypt meaningful messages, but just encrypt random messages. Then it should be hard for any efficient adversary, given a ciphertext, to recover that message. That's the RSA assumption, right? So even though RSA is not good directly as an encryption scheme, we believe that if all we were encrypting were really fresh random messages, then it is hard to break. Then it is hard to recover these random messages. Right, from this assumption, from textbook RSA, just encrypting random messages, we're building a key encapsulation mechanism now. So again, we have our RSA gen algorithm, and now we have a hash function which maps from Zn to strings of length lambda. So here's a question. Since private keys are random, encrypting them with textbook RSA is okay? The answer is no, or at least we don't know. But look at the, but you're asking a very good question that cryptographers started asking some 25 years ago. Here, it says choose a random R in Zn, and we're choosing that fresh and uniformly and independently, right? In particular, independent of E and D, right? That's a fresh random choice. You can't use E or D here. The experiment demands that you choose something fresh, random, that you haven't used before. Okay, and encrypt it. So encryption schemes which remain secure when you encrypt their own secret key. This is something we haven't talked about in this lecture, and I didn't plan to talk about. They're called circularly secure, right? This is something that normally shouldn't happen, something that only happens in sort of weird situation, that you use a public key encryption scheme to encrypt its own key. So in all the experiments that we've seen so far, this is not modeled. So in particular, typically the adversary doesn't get to, I mean, the messages that are encrypted are typically either chosen random or chosen by the adversary. The adversary doesn't know what the secret key is. But I must say, a very good question, right? That was a really good question here. All right. But the answer to that question is no. Good. So we have our textbook RSA keygen algorithm and a hash function which maps modular integers in Zn to binary strings of length security parameters. And now our key encapsulation mechanism, keygen ncaps dcaps, works as follows. So keygen is super simple. It just runs the RSA gen algorithm. So you get N, E, and D, where again, E and D are such, or E is chosen random, and D is such that E times D congruent 1 modulo phi of N. Encapsulation chooses a uniformly random R, right? A uniformly random and fresh R, and computes the ciphertext C as R to the E modulo N. It really just does textbook RSA encryption with this random R. Now we're going to output C, but also K, which is a hash value of R. Right? So on the one hand side, I'm choosing a random R and encrypt it with textbook RSA, which gives me this ciphertext C, and I'm also hashing R to get this symmetric key K. Okay, and I'm outputting C and K. Decapsulation is also not hard. Given the secret key and a ciphertext C, I'm first decrypting C by computing C to the D mod N, and then I am hashing it using this hash function H. Okay, and whoops, now correctness. follows easily, right? Just follows by the correctness of RSA. So when you have C equals R to the E mod n, then of course here you have your K, which is just H of R. But now when you decrypt it, you just have C to the D mod n, which is R to the E times D mod n, right? But now we know E times D is 1 modulo phi of n, so this is just R. So if we hash this, we get also here K equals H of R. And correctness follows. Okay, so correctness just really follows from correctness of textbook RSA. And then applying a hash function afterwards. But the hashing is deterministic. Okay, and now we're getting to the interesting point. Theorem 8.3, I'm calling this here. Assume that the RSA assumption holds. That textbook RSA is secure in that sense that we've seen earlier, given that we only encrypt random messages. If we look into our construction, this kind of looks good, right? Because the only messages that we're encrypting under RSA are these randomly chosen Rs. So assume that the RSA assumption holds, and assume further that H is modeled as a random oracle. Yeah, there's that. Recall that the random oracle was this idealized hash function, which on input a fresh, anything you haven't queried before, outputs a fresh random string, and you only get black box access to this hash function, right? That's there was this idealized modeling of hash functions. Applied cryptographers love this model because it allows for really, really efficient constructions like this one here, and for not too complicated security proofs. But as I've told you, theoretical cryptographers have a somewhat uneasy relationship with this random oracle model. But for now, let's just assume we have a random oracle. Then the keygen ncaps and dcaps algorithm I've just defined to you is an IND-CCA secure key encapsulation mechanism. So we have roughly 13 minutes left, and I'm just gonna sketch the proof ideas. Okay, so as a first thing, let's take the IND-CCA security experiment for a chem and instantiate it with these algorithms, keygen ncaps, dcaps, that we've just seen. So here we have our adversary A. And what does the challenger do? Well, the challenger generates NEND with RSA gen, or the textbook RSA keygen, chooses a uniformly random R star in ZN, right? Chooses a uniformly random bit B in 0, 1, or coin toss B. And now if B equals 0, we just set K, sorry, how do I call it here? K star equals H of R star. Otherwise, if B equals 1, we set K star to a fresh uniformly random value in 0, 1 to the lambda, right? And our adversary gets, of course, N and E. This is the RSA public key. He gets our, oh, I've forgotten the one of the most important thing. We set C star to be R star to the E modulo N, our C star, and of course K star. Good, but he also demands a decapsulation oracle where he can send these ciphertext C, and if C not equals, so actually now I'm, let me rewrite that. Otherwise, it's going to be, it's not going to look so nice. Since we're in the random oracle model, of course, he will get access to this random oracle H, right? But now he also gets access to this decapsulation algorithm or decapsulation oracle, which first checked if C equals C star, if C not equals C star. And if that's the case, it just sets R to C to the D mod N and K to H of R, and outputs this K. In the end, of course, the adversary returns this bit B prime. Zip. Right? And when if B prime equals B. So that's the IND-CCA experiment. IND-CCA experiment for our chem. Okay, good. Now that we've written this down, how could we possibly show, under the assumption that the textbook RSA assumption hold, or the RSA assumption holds, textbook RSA is secure when encrypting random messages, and that H is a random oracle, how could we argue security here? Can we maybe try to do that together? So what's the first challenge if we want to reduce this? If we want to use this adversary A here to break textbook RSA, what's our first challenge, or what's the biggest challenge here? Someone can tell me. Find collision, not quite, but someone else wrote the right answer. It's it's to decrypt C star. Well, the what about decrypting C star? No, let's say we want to use this adversary here to somehow break textbook RSA, right? What will we get in textbook RSA? Someone will give us N, E, and let's say some C star, okay? And with that stuff, you have to work. Our reduction has to work with N, E, C star. I mean, it seems kind of pretty straightforward to use instead of this N up here, to use that N, the same thing with E, right? To use E, and instead of using this C star, to use the one we're given here. But what's the issue now? Is this all that I need, or is this already sufficient? Let's say we were to do it this way. What's where do we, as a reduction, run into a problem? Look at this experiment, and is this information that we're being given here, N, E, C star, sufficient? Good. Someone wrote on the chat, it's the decryption oracle. Yes, this is the big issue, because to simulate or to implement the decryption oracle, we need this D. but we're not given D. So how could we possibly simulate a decryption oracle without knowing D? How could that be possible? This is somehow sort of the challenge for our reduction. It has to provide a decryption oracle without itself knowing D. How could we do this? Or what property of any of the components that we're using here could be used here? So I'm claiming that we can simulate this decryption oracle without even knowing D. And someone wrote an idea here which goes in the right direction. What we're going to use instead of that will be the random oracle H, right? And the random oracle H is used twice. Namely, the adversary is given direct access to it. And here we're also using the random oracle in the decapsulation algorithm. And that's what our reduction will use. The idea is the following. I think I'm not going to rush this through today anymore, but probably now I'm just giving really the quick idea, and I'll just write it up in the beginning of next lecture. But the idea is that if the adversary actually wants to know what the correct key here is, he first has to use whatever C to the D is, let's call it R. He first has to query the random oracle with R to get back some K, right? So in order to know whether the K that we're giving him here in the decryption oracle, whether that's actually the correct K, he first has to tell us what R is, right? But then if we already know what R is supposed to be, then we don't need D. Then we just need to if we already know the correct R that corresponds to the C, we just need to check whether R to the E equals C, right? For an R that we've already seen before from the random oracle. Good, that's the idea, right? We're using this called a pre-image awareness property, that's a technical term, of the random oracle. So for the adversary to even be able to detect whether we're giving him the correct answer to his decryption query, he first had to tell us sort of what the what this R, which is hidden in C, actually is by querying it to the random oracle H, right? Otherwise, we can just lie arbitrarily to him. Good. I'm still gonna write this down next time, but I think that's all for now. The quiz is gonna start in 2 minutes. Good. So here's still another question. Someone is asking, when will the last exam relevant lecture be? So let me put it this way. So in on a conceptual level, anything that we teach could be asked in the exam. But if you think about standard exam questions, They will cover this week and the next week. But the week after next week will mostly be relevant for, let's say, multiple choice questions. So you cannot just ignore what's being told to you in the last lecture. But again, what you're being told there will have significance mostly for multiple choice questions, but not for the, let's say, standard questions, which we ask every year. By the way, now remember, someone asked me to upload the old exams. I will just do that. I didn't get to do that. Someone asked me this Tuesday. But now it's time for you to take the quiz. So see you again on Monday. Let's wrap this up and then let's talk about digital signatures. Thanks, everyone.